Welcome everybody to the 6th unit of week 1 in the Parallel Programming Concepts course in OpenHPI. My name is Peter Tröger. After we now discussed the different terminologies and concepts that can be found in parallel hardware today, for example, as with symmetric multiprocessing, how multi-cores can be treated, what the role of the memory hierarchy is, and other aspects, we can now start to go deeper into the direction of software and ask ourselves, how do we target a particular problem, how do we optimize a particular application in order to exploit all these different parallel hardware resources. And if you want to do that, the first problem is to actually get a good understanding of what the target of software parallelization is. Let me give you an illustrative example. The example here is that you have two cars, a very fast racing car and some kind of van car, with a lot of storage space. And the simple question is, which one is faster? You can compare this question to the same kind of discussion you may have with your own software product. So you say, okay, I want to get this software faster, but what does it actually mean to get faster? What is the specific metric you can measure before and after your optimization or parallelization in order to claim that yes, you got a success and you became faster? And as you may already know, this discussion depends on your viewpoint. So a first viewpoint could be the usage scenario. When you take this illustrative example, if you want to transport a fridge, a racing car may be not your fastest option. Maybe the other car is a faster one. It may depend on your usage environment. So if you try to use the racing car inside a forest, you may not be as fast as with your van alternative. Or it may also relate to your perception of performance. So what means fast actually? Is it running faster? So in software terms, is it a faster overall execution time of the software? Is it about the average speed or computational speed you have in your software? Is it how good you can deal with additional data? So the point here is that getting software fast, getting faster by parallelization, getting speed up, is subjective thing that you must define for each and every piece of software you're actually targeting. However, despite the fact that benchmarking of speed improvements is an application-specific problem, there are common terminology terms that can be used to describe an overall effect. And these three terms we mainly want to use in this course are speedup, throughput, and scalability. So parallelism first can help in order to gain some speedup. Speedup means that you simply compute a given problem faster. For example, if you have some business calculation to do, some data analysis, speeding it up means that you get the same result with the same data in less time. Another aspect you may want to target with your parallelism is throughput, where you not really focus only on the speed of execution, but you mainly focus on the amount of work you can do in a particular time. And if you are able to compute more data items, more business analysis items, or whatever your target is, then throughput says that increasing the throughput brings you more computed, more processed data items in the same time in comparison to what you had before. Scalability, as the third term, is the idea of having software that is enabled to compute faster or maybe to compute more data items when you add resources. So scalability is a property of the software that says if the software is designed in the right way, then it is prepared to make use out of additional resources. And this scaling aspect is something that is very, very important today. One example is the big data environment, where the situation is that you have large, huge amounts of data that must be processed. So the software dealing with big data problems hopefully has inbuilt scalability in order to make use out of additional hardware resources you add to the system. You may achieve this scalability by using parallelism and parallel computing approaches, or for example, only concurrency mechanisms, and we will discuss them next week. In scalability, we further distinguish between two terms. They are not well commonly used, but most people agree upon that you can differentiate between scaling up and scaling out. Scaling up means that you take a shared memory system and you add more processing elements in the shared memory system. So it's basically about taking one machine and giving it more processing elements in order to have larger parallel processing capabilities. Scaling out, on the other hand, typically represents an idea where you say, I want to scale out my solution, meaning I add more machines to a shared nothing environment with multiple nodes, and I use all of these resources at the same time in order to improve the capabilities and the performance of my software. When we take these metrics now and try to bring them into a more formal setting where we can say, okay, maybe there's a way to think about them, there's a set of common concepts or a common understanding of how to interpret these terms. Speed up typically means that you add more resources in order to solve the same problem in less time. So the idea here is you have a piece of parallel hardware in whatever kind of setup, and you add more cores, more processors, or more machines in a shared nothing environment, and you get a faster result when you look into the same problem. The special version of speedup is linear speedup, which means if you add n times more resources, more cores, more processors, you get n times speedup. There's also an effect called superlinear speedup where you are able to even get more speedup than you actually added resources, which is typically due to caching effects. The other side is scale up, where we say with scale up we add more resources to solve a larger version of the same problem in the same time. So you add more processors, more machines, more cores, and this allows you to solve a larger thing, a larger set of data, to work with a larger problem while keeping the execution time more or less constant. Same idea again, with linear scale up, we have the situation then that n times more resources lead to an n times larger problem being solvable. And the question which of the goals is the most important one, this depends on the application. So for example, if you're aiming for throughput, then the thing you want to have is scalability, because you want to process more data at the same time in order to increase your throughput value. So depending on the application, you either head for speedup or for scale up in your application, and parallelism and parallel computation may help you with both things. Here's an example for a speedup scenario that helps us in getting a deeper look into the overall concepts. Let's take an application where we have a set of tasks being defined inside the application. Here in this example, we have exactly 12 tasks, and we have one processing element on the left side to compute these tasks. If we have only one processing element, we actually have to execute all the tasks one after each other. This is an idealized assumption with no other work being done on the machine or the processing element at this time. So if we take this idealized assumption, then we need exactly 12 time units to execute the overall application. On the right side now, we have the situation that we simply add more processing elements, parallel hardware, for example. And by doing this, we are now able to distribute the given work, the given task over multiple processing elements. We still have the same number of tasks. We still have the same number of tasks, but we have more processing elements, and this leads to the fact that we need less time to execute the overall application. The definition of speedup is now the comparison between the situation where we have only one processing element and the situation where we have multiple of them. So the speedup is computed by dividing the time needed with one processing element by the time needed with n processing elements. So in this case, we get a speedup of 3. One interesting aspect here is that if we take this idealized assumption of equal-sized parts, then the speedup is actually equal to the number of processing elements you use in your parallel setup. Reality is not ideal, so in reality we have several effects that hinder us from getting this kind of optional linear speedup, and one example for such an effect is the so-called load imbalance. Let's take the same application, but in this situation now we have the fact that some of the tasks take longer to be computed than other tasks. We still have a set of tasks that can run in parallel, but they're not all equal sized. And this now leads to the situation that, as you can see in the picture, the overall execution time gets a little bit longer because we have this overly long tasks that somehow hinder us from using the existing parallel resources in the most efficient way. So we get some of the processing elements being underutilized. They have over time some situations or some parts in time where they can no longer be used. This is an effect called load imbalance, and as you can see in the equation, this leads to the fact that speedup gets slower. So we no longer have a linear speedup, but we have sublinear speedup, and this is the effect you would see in practice typically, that you are not able to equally use all the available processing elements, but some of them are completely utilized and some of them are underutilized. Load imbalance is one relevant aspect we can find in the overall problem of speedup. Another relevant aspect with speedup are the so-called serial parts. Each application, each software application has parts that cannot be parallelized. What are these parts? What are examples for that? You may know them from your own practice. The most typical example is the application startup. So if you start to run your application, you first have to prepare yourself by, for example, loading data files or by creating a couple of threads in order to start the work. So this initialization phase is something that you cannot split up into different tasks that may run in parallel. So it's inherently serial. Then we have some part of the application that may be able to run in parallel, but then you may have a phase where you need to work with intermediate results, for example, to sum them up or to get some intermediate feedback for the user. And these are algorithmic or control flow limitations that lead to the fact that, again, we have a serial part in the execution. So in real life, software applications consist of parallel and sequential parts. That's the one aspect of speedup. And the second thing is they may not all be equally long. If we now take these two things and combine them, we end up with a situation where you have to consider both aspects in order to figure out how good you can get with a particular speedup. And this kind of relationship was formulated by Jean Amdahl in 1967 in the so-called Amdahl's law. The original paper only has a small comment about this relationship, but later people formulated in an overall equation that is now a commonly accepted and very relevant aspect of parallelization. So Amdahl's law basically says we have a given program, a given piece of code, and we have the particular serial parts and the parallelizable parts. They may not all be equal sized, but the main thing we're interested in is the sum of all serial parts in terms of execution time and the sum of all parallelizable parts. The execution time for the application, according to Amdahl's law, with one processing element now simply is the combination of all the serial and the parallel parts. If you execute them one after each other, you get the sum of them, and this is the overall execution time you need to finish the application. If you now take a parallel resource, a parallel computer, and start to distribute the parallelizable parts on different processing elements, you come into the situation that the portion of time you spent in a parallelizable part is now split up between the available processing elements. So what we do here is we divide the big T par value, the time we need for all the parallelizable parts, by the number of processing elements we use. And this gives us an overall application execution time. And when we have no load imbalance, the sum is actually the real execution time you can get. If we have some load imbalance effects in the system, then it may take even longer than the sum of these two factors. And taking this relationship of the different values then ultimately leads to Amdahl's law for the maximum speedup you are able to get with n processing elements. So you take the non-parallel run of your application, you take the parallel run of your application, and you want to figure out how much do I get from investing a number of resources n in order to get some speed up. And Amdahl's law now says this value is the relationship between the execution time without using multiple processing elements and the execution time that you have when you use multiple processing elements. So this is T1 divided by Tn. When you take this formula from Amdahl's law and you plot it into a graph, like here, you see an interesting effect. So here we see a logarithmic scale on the x-axis for the number of processors. So we exponentially increase the number of processors, and we see different curves for a particular amount of p, which is the parallelizable part. And you can see here that depending on the amount of parallelism you have in your code, the extent of the parallelizable part, you have a particular increase in the speedup when you add more resources. So adding more resources gives you more speedup, which is a good thing, but this effect is capped. So there is a particular point, a particular number of processors where you no longer get more speedup by adding more resources. So adding more processing elements, more cores, more machines doesn't give you any more benefit according to Amdahl's law because the speedup is capped. And this effect is independent from the amount of parallelizable code. It may happen later when you have more parallelizable code, but ultimately there is always a point in time where the speedup you can get from adding more resources doesn't help you, is limited, and you no longer get any kind of speedup. Why does that happen? Where does this come from? The reason for this is that the speedup you get according to Amdahl's law is limited by the serial part. So the serial part is actually the bound you have when you increase the number of resources constantly. You can see this here in this formula. Going with n towards infinity actually leads to the fact that the speedup is limited by the serial parts only. So how good you are in the parallelization doesn't matter, since the overall execution is still bound to the serial parts you have to execute anyway. So if you imagine yourself a system with an unlimited amount of cores or processors, you can do all the parallel work in the minimum amount of time, but this doesn't save you from still doing all the serial parts you can't get rid of. So the parallelization problem, the speedup problem in software, according to Amdahl's law, actually boils down to the fact that you need to take care of your serial parts. What are these serial parts? We saw that these parts may be bound to the software algorithm or initialization, but this may be also a limitation from hardware components, from the operating system, from the virtual runtime environment, from the middleware stack. So there are different sources of serial parts that actually block you in the usage of new cores or new processors in your system. Amdahl's law had a tremendous effect when it came out in '67 on the parallel computing community, because basically everybody said, okay, let's stop building parallel hardware. This is not really useful, it doesn't make any sense, since when we invest all the time in adding new processing elements into the system, it doesn't pay off anyway, because we can't get more speed up at some point in time by adding more resources. Thomas Prusek from IBM also once said, everyone knows Amdahl's law but quickly forgets it. So this is also an effect that is well accepted, but many people still try to do parallelization and expect some kind of linear speedup by just adding more cores to the execution environment. Amdahl's law says us that, for example, if you have 90% parallelizable code, you can't get more than 10 times speed up, regardless of the number of processing elements you use. So the overall result from this paper and this law was that parallelism is basically only useful if you have a small number of processing elements or if you have highly parallelizable code with very small serial parts in it. And this was somehow disappointing for the parallel computing community, but there are a couple of assumptions in Amdahl's law that make this less critical. The first relevant assumption in Amdahl's law is that we have the assumption of fixed problem size. So Amdahl only talks about taking the same problem and running it on either one processing element or multiple. So the problem size, the application, the amount of data being processed is not changed at all. The second point is that Amdahl only talks about the overall execution time for one problem. So there is no other interesting factor here than how fast is this application done. And these two investigations actually lead to a second law called the Gustafson-Barsis law from 1988, which was way later. And these two researchers identified that even though we have Amdahl's law and it is valid, There's a second fact, and this fact is that people sometimes are not only interested in the overall execution time, but with adding more resources, they may be interested in solving a bigger problem. For example, computing more data, running a more fine-grained simulation with more details. So Amdahl's law holds, but maybe the goal of Amdahl's law, the execution time factor, is not the only thing that counts. So Gustafson and Barsis declared that we could do the following thing. We could add more processing elements, more resources, but at the same time we could also increase the problem size. So you use more cores and more processors in order to actually compute more data, like in big data environments, or to work with a larger mathematical problem. And this is a typical thing that you can find in the high-performance computing area, but meanwhile also in standard business and desktop environments. You increase the problem, or the new resources enable you to work with an increasing amount of data or with a bigger problem size. When you take this consideration and try to put it in a formula similar to Amdahl's law, you get something that is called scaled speedup. And the scaled speedup is the relationship between the serial parts we still have and the parallel parts, but this time we consider the additional number of processors as an advantage. So the scaled speedup tells us that as long as we can keep the serial fraction more or less constant, we can increase the number of resources and we still get nearly linear speedup by using all the parallel resources. The serial part here plays an important role because the usability of additional resources for the parallel parts is accepted, but the question is, why don't you get larger serial parts when you increase the problem size with increasing n? And it turns out in practice that this assumption of a non-growing serial part, even though you increase the problem, is mostly valid. When you, for example, see that serial parts are initialization or synchronization points in your code, then this doesn't change when you simply increase the amount of data being analyzed in parallel. So if you have, for example, a computational problem, you still start up your application, that's a serial part. You load your data, that's a serial part that takes more or less the same time. And then you have more computational steps or more data being processed in the parallel part. So in practice, it turns out that if you are able to ensure that the serial fraction remains more or less constant, you can let your problem grow with the additional resources, and this allows you to get endless speed up when you are able to add endless resources. And these two laws form the foundation of what we currently have as parallelization measurement or speed-up measurement. There are other models, more complex models, that are also closer to reality. Examples are the work-span model or the cup-flat metric. But these two laws, the Gustafson-Barsis law and the Amdahl's law, they form the foundation of what we currently know as speed-up and the speed-up problem. Okay, this was the last unit for this week. As a summary, what did we talk about during the whole week in the Parallel Programming Concepts OpenHBI course? We first covered Moore's law and the power wall, and we discussed how processing element speed no longer increases. So due to different hardware effects and trends, we are now facing the situation that the only offer hardware people can make us in order to get faster software with new processing hardware is to use additional cores. So the transistors delivered from Moore's law now end up in additional cores per processor chip. We also have different combinations and memory hierarchies. So this is the way to go if you want to speed up your computation. If you want to have faster software in the future, then you need to exploit these hardware capabilities. In this week, we also talked about a set of acronyms and terminology in order to get common concepts in this course. So we talked about ILP and SMP, different strategies of having parallelization or parallel processing elements inside the hardware. We talked about Flint's model of dealing with instruction streams and data streams. Another aspect we talked about is the question of memory hierarchies and how they either have a uniform or non-uniform access time when coming from different processing elements. And at the end, we talked about Speedup and Scaleup, which are expressed as concepts by Amdahl's law and Gustafson's law. And for the upcoming second week, one interesting question will be, since we need the parallelism for Speedup, which you hopefully can agree upon now, how can we express this level of parallelism in software? And with this, I would like to thank you for your attention and hopefully see you next week.